Today we want to become a bit more familiar with our current transformer model. Now we'll talk about the different types of this plot here. It's called saturation curve. It also can be named magnetization curve or magnetizing curve according to IEC standard. In the technical literature, we can often find the following representation of the magnetization curve. The curve is usually shown in a BH diagram. Here we see an initial magnetization together with a hysteresis curve. It is surely all correct, but the practical approach has led to all this being gradually simplified. In the end, a rectangular magnetization curve emerged as the simplest type. However, these simplifications were not adopted without a reason. With certain assumptions, a rectangular magnetization curve can be trusted instead of this complicated curve. As far as the quantities on the axis are concerned, the magnetic flux density or induction B in Tesla is usually shown on the y-axis, and the magnetic field strength H in ampere divided through meter on the x-axis. If, however, we aren't just talking about a piece of steel that is about to be magnetized, then other quantities are often shown on the axis. For example, on the x-axis, magnetomotive force mmF in ampere turns, or the magnetizing current IME in ampere. On the y-axis, on the other hand, the flux phi in Weber and the flux linkage Psi also in Weber can be placed instead of the induction. The quantities on the axis are proportional to each other. Hence it is basically a scale change. The quantities Psi and IME were chosen for the model because they are those quantities that make the least demands on the initial data. This means that the dimensions of the current transformer need not be known. If you want to have a magnetization curve where the flux is represented on the y-axis, then you would have to introduce the number of secondary turns Ns. Alternatively, for the induction B, one needs to know the core cross-section A. The situation is similar with the x-axis. For mmF, one would have to know the number of turns. For H, the mean path length L of the magnetic core. For the calculation of the saturation time Tsat though, we don't need these additional parameters, since we can simply use the flux linkage Psi and the magnetizing current IME. Let's now recall what the connection is between the flux linkage Psi and the magnetizing current IME. It is the inductance L. That is, Weber results from Henry multiplied by ampere. Consequently, the inductance corresponds to the inclination of the magnetization curve. We could also say that the inductance is proportional to the tangents function of these angles of inclination. Let's call them alpha. Therefore, we can denote this part of magnetization curve with Lm1 and this one with Lm2. These inductances thus determine how the magnetization curve sections are inclined. Using the current transformer equivalent circuit diagram, it is now possible to show what influence these two inductances have and also to derive 4 different types of the magnetization curve. So, this is the equivalent circuit of the current transformer. Here we have the primary current, that is the short circuit current. This is the magnetizing current IME. Here is the secondary current that our protection device measures. Here is the leakage inductance of the secondary winding, X sigma S. This is the ohmic resistance, RCT, of the secondary winding. Here are the inductive and ohmic components of our burden, XB and RB. With these quantities, the resistance of the wiring, the protective device, or any terminal resistances are taken into account. Though at this point we are only interested in the magnetization branch, because there is a nonlinear inductance here. This nonlinearity is described in the present case with the two linear inductances. If certain assumptions, like for instance neglecting the hysteresis, are made, this dependency can also be recorded as follows. The magnetizing branch consists of two inductances connected in series, one that can be expressed as Lm1 minus Lm2, and the other as Lm2. Here we have a switch that closes when the current of flux linkage exceeds this point. It means that if the operational point is in this section, the switch is open and the total inductance of the magnetizing branch is equal to Lm1 minus Lm2 plus Lm2, that is Lm1. If the knee point of the magnetization curve is exceeded here, the switch closes, this branch is short-circuited, and only the inductance Lm2 remains. This procedure allows us to jump from Lm1 to Lm2. Now we'll derive the four following types of magnetization curve from this branch by letting the corresponding inductance of this branch go either to 0 or to infinity. Let's now look at these four curves in detail. We won't trace the secondary branch each time, as everything remains constant there. We'll only draw the branch with the magnetizing inductance for two operating cases. On the left is the normal operating condition, on the right the operating condition if the CT is saturated. The first type is the general case. Here we have Lm1 in normal operation and Lm2 in saturation, as can just be seen here in the magnetizing curve setting. With the second type, we can let Lm2 go to 0 here. This is the inductance in saturation mode. So Lm1 remains, while Lm2 goes to 0 and short circuits the secondary branch. The magnetizing curve of the third type looks like this. With this type, we have an inductance Lm1 in normal operation that tends towards infinity. The current flowing through is 0. In saturation mode, on the other hand, some residual inductance Lm2 is still there. With the last type of magnetization curve, which is the simplest in terms of calculation, but at the same time also one that is subject to the greatest error, the magnetizing branch is interrupted in normal operation and short-circuited in saturation mode. The magnetizing curves can be changed with the mouse as well as with the time constants Tm1 and Tm2 in the input field. Tm1 and Tm2 are time constants that are related to the inductances Lm1 and Lm2. They are connected to each other by the resistances RCT and RB. So if you divide Lm1 or Lm2 by the sum of RCT and RB, you'll get Tm1 or Tm2 respectively. In normal operation, the inductance is ideally very high and the current transformer core is far from being saturated. Therefore, we have very high time values for Tm1, for instance hundreds of milliseconds or even seconds. As for Lm2 and Tm2, it's just the opposite. The time values must be very small. For the last type of magnetizing curve, this time is even 0 milliseconds. You can also change the two time constants with the mouse wheel. For fine adjustment, the shift key can be used as usual. The remanence can be entered with the help of the remanence factor Kr. It corresponds to the ratio between the remanence flux Pr and the saturation flux Ψsat. It can be changed with the mouse, but also in the input field. What is worth mentioning here is this horizontal line representing the saturation flux Ψsat for curves number 2 and 4. This is the flux linkage caused by a current that results from the multiplication of the secondary rated current and the accuracy limit factor ALF for a given current transformer, the parameters of which are specified here in the input fields. So if we take the rated data of the current transformer, that is the rated burden, and we make an assumption that the rated short circuit current flows on the primary side, meaning that the primary rated current of the current transformer IPN is multiplied by the factor ALF, and we further assume that this current is transferred to the secondary side without error, then it is the maximum flux linkage that can occur. If the flux linkage becomes higher, then the current transformer goes into saturation. That's why this line shows the saturation flux Ψsat, a limit according to which you can set the magnetizing curve of the current transformer you have selected. If we shift the curve upwards, it will cause the current transformer to saturate later, because we are improving the magnetic property of its core, so to speak. The higher is this flux linkage, the higher is the flux density of the current transformer core. If we shift the curve downwards, we worsen these properties and hence reduce the saturation time. The last important point is the scale change. With the primary quantities, we have a uniform scale, because on each axis the unit is ampere. We turn the mouse wheel and the scale changes simultaneously on both axes. Here, however, we have the unit ampere on the x-axis and Weber on the y-axis. Therefore, the scale must also change independently. As soon as you move the mouse point to the upper left of the plot, a vertical double arrow appears, indicating that you can change the flux linkage with the mouse wheel. If you move the mouse pointer to the lower right part, a horizontal double arrow appears there, indicating that the ampere values on the x-axis can be changed. As before, the Shift key can be used for fine adjustment. As for the magnetizing curve of the model, that's probably it. If you have any questions, then don't hesitate asking in the comments below. In the next video, we'll look at the time-dependent current waveforms. Thanks a lot for your attention. See you in the next video.